Here's another heat transfer problem. I got a liter of water at 30 degrees C to make iced tea. That's like a little hotter than room temperature. How much ice at 0 degrees C must be added to lower the temperature of the tea to 10 degrees C? And it gives me the specific heats in calories, right? So let's think of the energy transfer. So I have some water, right? And I want to lower the temperature of the tea is water, right? So we'll just call it water. So I'm going to lower the temperature of the water. So the heat lost by the water, right? Where's that heat going to go? Well, the heat is going to go to the raising the temperature of the ice. So first it's got to melt the ice. So it's Q to melt the ice. And also it's the heat to raise the temperature of the ice from 0 to whatever, 0 to 30, or no, 10, right? So you're going to put the ice in. It's going to take some of the heat in the water and it's going to convert it to melting the ice. And then it's going to raise the temperature of the ice from 0 to 10, right? And that's going to be equal to the heat that the water loses in going down from 30 to 10. Okay, now that we got that out of the way, we can go write an equation, right? So let's look at what this looks like. So the heat lost by the water is going to be MC times delta T for the water, right? MC delta T equals the heat to melt the ice is latent heat. So that's the mass of the ice times the latent heat of fusion of the ice, plus the heat to raise the temperature of that melted ice from 0 to 10 after it's melted, right? So it's still the mass of the ice, right? Because I put this ice in, it's going to turn into water. So the mass of the ice that turned to water times the specific heat of the water times the delta T of the ice. And so we've done this before, right? It helps to make a table of like what's what. So what do I know in here? I know the mass of the water. I know the specific heat of water, right? I know the delta T of the water. I know the delta T of the ice. And I know the latent heat of fusion of the ice. So the mass of the water, right? So how much ice? 1 liter of water. So 1 liter is 0.001 cubic meters, right? Or that's 1,000 grams. So which one am I in? I'm in grams. So I'm going to call 1 liter 1,000 grams of water. It's a nice thing about water. It just straight up converts. Specific heat of water, we already know it's 1 calorie gram degree C. So that's 1. My change in temperature of the water. My water is going from 30 to 10. So that's a change of 20, right? My ice is going from 0 to 10. So that's a change of 10. And my latent heat of fusion is 79.7. So I'm going to call that 79.7. And now I can take this, and what am I trying to solve for? I'm trying to find how much ice, right? So I'm trying to find mass of the ice. So I've got to do a little bit of algebra, but it's not too bad. So I can show you before I do it, right? See how these both have MI? That's the mass of the ice. So I can pull both of these out, like reverse distribution, I guess you could call it. So I'll do mass of the water, seawater, delta T water equals mass of the ice times the latent heat of fusion of the ice plus specific heat of water times delta T of ice. I don't know why I wrote ice. I wrote I for everything else. Whatever. And now I can solve for the mass of the ice, right? So you can just move that over and you know all your stuff, right? Mass of the water, specific heat of the water, delta T of the water, what the hell is it called? The latent heat of fusion, specific heat of the water, change in temperature, right? You're done, right? All you got to do is solve that. And because you left everything in calories and grams, right? I did that in grams. I don't need to convert anything. I'm going to get it in grams. So not too bad. It's just to start it, you have to think about like what's happening with the energy. So in this case, the water lost energy. And it was gained not only by melting the ice, but also taking that ice and raising it from 0 to 10.